we have intuitively seen that the resistances combined in series would be effectively a greater resistance. Now we have to find the exact numerical value how much it would be. Like a 2 ohm combined in series with 3 ohms will result in how many ohms? 5 ohms, 6 ohms, 4 ohms. It is greater than 3 we know, but how much? And we have to derive it. The way I am going to show you how we derive the effective resistance or the equivalent resistance of resistances combined in series, you are going to do the same steps to get the resistances combined in parallel. So I am not going to derive it for you. First you will have to derive it by yourself for parallel. And series also I'll give you hints so that you can do it yourself. So basically what we are doing is we have two resistances, say R1 and R2 in series, and we need to know what is the effective value of those two resistances as a single resistance. So what we have done is we have added a battery from my own side, from our own side we have added a battery to check what resistance on adding the same battery. This is V volt battery, this is also V volt battery. On adding the same battery will give you the same flow. Say I current is flowing over here, I current was flowing over here, and the same I current flows out of the battery over here. So this was R1 and R2. This R equivalent should be how much, such that the same battery gives you the same current. So if we can figure out that value, we'll call this resistance as the equivalent of these two resistances. Now before we derive the formula, let me give you this as a numerical question, and using the basics of Ohm's law, I think you would be able to solve it. So say this is the question. I have a 2 ohm resistance in series with a 3 ohm resistance, and there is a battery of say 10 volts to push the current through this. So my question is, how much current is coming out of the battery? I'll give you a recap on the basics. The current, whatever is coming out of the battery, has to go into the battery on the other side. The current, if it has no other paths to go to, it will go through the resistance. How much ever current is entering the resistance, the whole will go through it, and then the whole of it is going to go through the other resistance also. It is not that the current in this would be more than the current in that. Whatever is the current here is the current here, is the current here, is the current here, is the current here. Due to the resistances, the current is reduced overall in the whole circuit, not at points. If I have another parallel path, that may have some other current and this will have some other current. But this is the only path, that's the only circuit. So in this only loop or circuit, the current all over would be same. And the potential concept you already know. So to figure out the current in any resistance, ultimately you'll require the Ohm's law, which is V is equal to IR, where V is the potential drop across a resistance is your V, I is the current in the resistance, and R is the value of the resistance of that resistor. I'll give you a minute to solve this. I hope you have got it. Let me also work this out and you match your answers with mine. So I'm going to mark the potential points. The potential difference across the battery is given as 10 volts. So for ease of solving, I'll call the potential at this point as 0 volts and the potential here as 10 volts. So this whole line till here has the same potential. I'll call this point as A and this point as B. So this point is also like A. VA is equal to 10 volts. Now B potential is same as all over here. So again VB, this point is also B, all these points are B, and VB is equal to 0 volt. VA was 10 volt, VB is 0 volt. I don't know what's the voltage over here. Say this point is C. So all these points are C. I don't know VAC. If I knew how much is VAC, it was very easy for me to find out what is the current in this. But I know one thing. I know that the current in this resistance is equal to the current in that resistance. What I can say is that the potential drop across this resistance VAC would be equal to, that's your VAC, would be given by Ohm's law and would be equal to the current in this into the resistance of that. So current in that is, say, I into the resistance, which is 2 ohms. So the potential drop across A and C is 2I. Similarly, the potential drop across this 3 ohm resistance, which is VCB, it will be equal to the current in the resistance into the resistance of that resistance. Now current in that resistance for sure is the same I, it's the same I as this one. This I and this I is same into the resistance of this resistance, which is equal to 3. So the voltage drop from A to C is 2I and the voltage drop from C to B is 3I. So what do you think is the voltage drop from A to B? Yeah, you're right. Voltage drop from A to B would be equal to voltage drop from A to C plus voltage drop from C to B, which will be 2I plus 3I, that is equal to 5I. That's the voltage drop across A and B, but A was the same point as this A. All this is same potential, and B here is the same as this B. So we already know what's the potential drop or what's the voltage across A and B. The voltage across A and B is already given. It's the voltage of the battery, which is 10 volts. Hence, we know that 5I is going to be 10 volts. So we have 10 is equal to 5I and I is equal to 10 by 5, which is 2 amperes. Now we got our current which is going to flow through this or that. So that's 2 amperes. So if I ask you what is the effective resistance, had there been one resistance instead of two, what value of resistance would you have chosen? So let me assume that the two resistances would be equivalent to this resistance over here, and I'll call it as R equivalent. Let me put the same battery, the same 10 volt battery across this resistance, and for this resistance, this R equivalent to be same as the 2 ohm and 3 ohm in series, the current drawn from the batteries should be same. So earlier the current of 2 ampere was getting drawn, again the current of 2 ampere should get drawn. To figure out R equivalent, we have to use the Ohm's law, which is V is equal to IR. Now as I've told you, it works for resistance. We should know the voltage across the resistance and we should know the current in the resistance. Then only we are going to get the value of the resistance. Among the three of these things, V, I and R, we should know at least two to get the third one. So do we know the current through the resistance? Yes, we know it. We know that the current which is coming out of the battery has to reach back all over the circuit. The same current is flowing, which is 2 amperes. So across any given point, 2 amperes current is flowing, and that is the current through the resistance also. Now do we know the voltage across this resistance? Yes, we know that also. The voltage across the resistance is the same as the voltage across the battery. Why so? Because this end of the battery is same as this point. There is nothing in between from this point A to that point A. And that end of the battery, say point B, is same as that point, point B. There is nothing in between. Hence the potential at A and potential at B is known. The potential difference across AB was 10. The potential difference across here also would be 10. So among the three things, we know V is equal to 10, I is equal to 2, and hence your R is going to be 10 by 2, which is 5. So we are going to get our R equivalent is equal to 5 ohms. So we see that a 2 ohm resistance and a 3 ohm resistance, when combined in series, results in a greater resistance, and the value of which is a simple addition of the two resistances, which is 2 plus 3. Now if you have more resistance in series, you can simply keep on adding using the same logic. Now to derive it as a formula, we have to take variables instead of numbers. So with variables R1 and R2, we are going to do the same process and get the R equivalent value. So we are going to put a battery from our own side, call it as a V voltage battery, and see how much current is getting drawn. If I current is getting drawn, here the same current should get drawn with the V volt battery. So I'll give you 2 minutes to do it yourself, and then I'll do it on the board. You just cross check whether you have done it right. So I hope everybody got it. We have to basically keep on applying V is equal to IR, the Ohm's law, properly. So here, as it is proposed, let I current be coming out of the battery, then how much must be the current in this resistance? It should be I. What should be the current in this resistance? It should be I again. So resistance of the resistor is R1, the resistance of the other resistor is R2. So what do you think is the voltage across the first resistance? Say V1 would be equal to current in that, which is I, into the resistance value, which is R1. Similarly, the voltage drop across the resistance R2, call it as V2, would be equal to the current in there, which is I, times the resistance, which is R2. So we see that the voltage drop across the first resistance is V1 and the voltage drop across the next resistance is V2. So the total voltage drop from this point to that point, let us again label the points. Say this point was A, so this is again electrically it is the same point, so it is also A. Say this point was B, so this point is again B. This point is neither A nor B, so let us call it as C. So VAC is your V1 is equal to IR1 and VCB is equal to V2, which is IR2. VAB is the same as the voltage across the battery, and the logic is what we have discussed earlier. So in this circuit we can write V, which is the voltage of the battery, is equal to V1 plus V2. V is equal to VAB and VAB is V1 plus V2. It drops by V1 voltage from A to C and further drops by V2 voltage from C to B. So the total drop from A to B is V1 plus V2. So that is what we get from the first circuit. We can write in terms of current and R1. So that is equal to I R1 plus I R2. Now let us go on to the equivalent circuit. So the equivalent proposed circuit is again the V volt battery, current coming out is I, and instead of two resistances it is R equivalent. So to make the equation over here, it's quite simple. The voltage across the R equivalent would be same as the voltage across the battery, because that's the only resistance in the circuit. This point is that point and this point is that point. Voltage across the battery is V, so voltage across the resistance is also V. So your V is your VAB basically, and the current in the resistance is again I, because I current was coming out of the battery and I current has to reach back to the battery. I current was all over the circuit. So the voltage drop given by Ohm's law would be V is equal to I R equivalent. So we get over here is V is equal to I R equivalent. Is this V and this V same? Yes, we have used the same battery. Is this I and this I same? Yes, we have said that we are using such a resistance such that the same current comes out so that it can be called as the equivalent resistance. So can we equate the two? Yes, we can equate the two equations. The equation over here number 1 and equation over here number 2 can be equated, and from equation 1 and 2 what we get is I R1 plus I R2 is equal to I R equivalent. So taking I common and cancelling all over, we derive the major formula. R equivalent in series is equal to R1 plus R2, the resistances which were in series. I hope you have understood. I hope you have got it yourself. Our next job is to get the resistances, the equivalent value of the resistances when they are put in parallel, and we are hoping to get a value which is lesser than the minimum one in the parallel. Now let's try to get what is the equivalent value of resistances in parallel. So if you have say 2 or 3 resistances which are in parallel like this, say R1 and R2, then effectively they can be replaced with a single resistance of what value are equivalent. So that's the question. These two resistances is in fact what value single resistance. Now I propose you the same method of solving this circuit also as you have done for series. You'll put a battery of V voltage across this circuit and then put a battery of same voltage, same V voltage across this circuit. In both the circuit, the current drawn from the battery should be same. So in fact, before going on to solve that circuit, I'll give you a numerical where you don't have the formula yet and still you can solve it. So that's your question. There is a 2 ohm resistance in parallel with 3 ohm resistance, and they have been put across a battery of say 6 volts. Now my question is, what should be an equivalent resistance of these two? So before you do that, I would like you to find out what's the current drawn from the battery, what's the current over here, I, and what are the currents individually in the branch, say I1 and I2. If you get those things, you'll get the equivalent resistance also very easily. So I'll give you some time to do it. Do it through basics, the fundamentals which has been told, and you'll see it is very, very easy to solve. The basic is the points which I told you earlier, and V is equal to IR, where again I'm telling you V is the voltage across the resistance, R is the resistance of the resistor, and I is the current through the resistance. So I hope you have managed to get the answer. So let me also solve it. Again, studying the potentials and tracing how the current would be going. Say the potential over here is A and potential over here is B. So voltage of the battery V is in fact VAB is equal to 6 volts in this case. So which all points are A? This is A. All these lemon yellow points are A in fact, because there is no potential drop. This point is A. I hope you agree. Then there is no potential drop from here to there. So this point is again A. There is no potential drop from here to there. So this point is again A, as has been told earlier to you. And similarly, if this is B, all these pink dots are the same equipotential point, which is B. So this is your B, that's your B, this is also your B. All these is B. Now to get the current in any resistance, we need to know the voltage as well as the resistance. So again, between the three things, V, I, R, if we know any two things, then we can get the third thing. So for this resistance, do we know any two things? Yeah, we know. We know the resistance of this resistor. We know the voltage across the resistor. The voltage across the resistor is same as the voltage across the battery. There is immaterial whether another resistor is there in parallel or not. The voltage across this resistor is 6 volts. Similarly, the voltage across that resistor is again 6 volts. The resistance over here doesn't change the voltage across the two branches. So that's good for us. So it's a very simple question in fact. What we see over here is, for this resistance, say R2, for that resistance, we apply V2 is equal to I2 into R2. And for that resistance, we'll apply V1 is equal to, V1 is the voltage across the resistance, V1. V2 is the voltage across this resistance, that is V2. So V1 is equal to I1 into R1. So what is I1? I1 we don't know. What is R1? R1 is 2. What is V1? V1 is 6 volts. 6 volt across the battery has appeared across that resistance also. So what do we get over here? 6 is equal to I1 into 2. So the current in that resistance is equal to 3 amps. Similarly, the current in this resistance, your V2 is again 6. Why V2 is 6? Because the voltage is again the voltage of the battery. I2 and R2 is your 3 ohms. So what is I2? You get your I2 is equal to 2 amps. So we know the current in each branch. In fact, if we would have used some formula to get it, we wouldn't have known the current in each branch. You would have known the total current. So formula is not advised to be used in such simple cases. It is much easy to do it simply. It is much easy to do it by the fundamentals. You know the voltage, you know the resistance, you want to get the current in it, you use the Ohm's law and you'll get it. It'll get complicated when you don't know the voltage across it. When would you not know the voltage across it? When there are some other things in between, say a resistance over here or a resistance over there. But here, there's no issue, no problem at all. So, what do we get the total current as? We get the total current I is equal to I1 plus I2, because this I current split into two, became I1 and I2, which is 3 amps and 2 amps, and went across the resistance, and then again they are joining back and will again appear as 3 plus 2, which is equal to 5 amps. So 5 amps will go into the battery. So what is coming out is also 5 amps. 5 ampere came out and 5 ampere went in. So we are not yet done with the question. The question was, what resistance would you replace these two with? So what we do, we'll make an equivalent circuit. Equivalent circuit would be something like this. A single resistance instead of two, and we are hoping to get a resistance which is much lesser than the two resistance. I mean lesser than the least one of it. It is not going to be more than 3 for sure. It is not going to be between 2 and 3. It is going to be lesser than 2. Why it is going to be less than 2? It is going to be less than 2 because if 3 was not there, if that 3 was not there, then the current which would have gone through would have been 6 by 2, which is 3 amps. So if this 3 ohm resistance is there, some extra current is going. If extra current is going, that means the total resistance of the circuit has decreased. So we are going to put again the same battery, which was a 6-volt battery. It's the same battery, and our logic is that if the same current, which is 5 amps, is going to come out of this battery, then this resistance, R equivalent, must be equal to the effective resistance of those two. So we have to figure out how much is this. Now that's again an easy job, I hope. This you would have done it mentally already. The resistance is what we need to find. We already know the voltage across it, which is 6 volts, because this point is this point and this point is this point. So voltage is 6 volts, and the current in this is 5 amps. We apply the Ohm's law across the resistance. The Ohm's law tells us that V is equal to IR 6 is equal to 5 into the R equivalent. So we get our R equivalent as 6 by 5 ohms, which is 1 by 5 ohms. So is it not coming less than the lesser of the two? It is lesser than 2. So it must be right. So can you proceed in the same way and solve this one? Derive a formula for it? I hope you can. I'll give you 2-3 minutes for it. Go for it. So yes, let me complete the circuit. Put a battery. Please note that no battery was initially given. We are proposing this logic to get the answer what we are seeking. So the battery has to be same and the current coming out of the battery has to be same. That's the logic. So here again the current split is I1 and I2. We don't know I, we don't know I1, we don't know I2, we know R1, we know R2, and we have proposed some V. So we don't know V also, but it's the same V here and there. So again, using the previous logic, this point is A, that point is B. So here this is A, that is B, this is A, this is B. Voltage across AB was V. Voltage across AB over here is also V. Voltage across AB over here is also V. This voltage is V, same as the battery voltage. This voltage is V, fortunately same as the battery voltage. So what's the current in there? The current in there, the same steps what we were doing over there. The current over there, say the first resistance, I've named I1 and I2 in the opposite branches. So this is 2 in fact, and that one is, it has dried up, that's 1. So the current in the branch 1 will be again given by V 1 is equal to I1 into R1. So what is V1? V1 is V, voltage of the battery. I1 is what we want to know, and the resistance is R1. For the lower branch, again V2 is equal to I2 into R2. So V2 again is the same voltage as the battery voltage. I2 is what we are seeking, is equal to R2. So that's it. We are almost done over here. And the total current, yeah, I will be I1 plus I2. That's your I. I will be equal to I1 plus I2. We may write it over here. I is equal to I1 plus I2. So from equation 1, you call it as equation 1, and this is equation 2. What we get is, from 1 and 2, what we get is I1 is equal to V by R1 plus same V by R2. That's your I. This is what we get from equation 1 and 2. That's what we get. Okay, let's go on to our other circuit. In this circuit, again we have to write the Ohm's law. The voltage across the resistance is V, the voltage of the battery, which is same as this battery, and the current is the only current which is flowing all along the circuit is I, what has come out of the battery. So applying Ohm's law over here, what we get is V is equal to I R equivalent. So what's the current over here? Current is V divided by R equivalent. What was our logic? Our logic was, if we use the same battery, it should be the same current. So this current and this current is same. So this current and this current is same. If these two currents are same, then we may write from here and here that V divided by R equivalent is equal to V divided by R1 plus V divided by R2. So it's the same V. So you can take common and cancel it out. So this is what we are getting ultimately. So this is going out of the board. I'll write it over here. 1 by R equivalent is equal to 1 by R1 plus 1 by R2. So that's your formula when the resistances are in parallel. Would you like to check the formula? We just found out that if the resistances were 2 and 3, then the effective resistance would be 6 by 5. Is it right? Let's try out the formula. So using the formula here in this space, 1 by R equivalent, this R equivalent should be equal to 1 by 2 plus 1 by 3. So what do we get? Taking the LCM, we get 3 plus 2 by 6, which is 5 by 6. But don't be in a hurry. Don't think that resistance is 5 by 6. Resistance, this is 1 by R. 1 by R is 5 by 6. So the resistance, equivalent resistance is 6 by 5 ohms. That is exactly what we got. So had we solved this question using the formula, the sequence would have been, these two would have been reduced to 1. We know the formula, hence we would have got the resistance value, which is equal to 6 by 5. Now knowing the resistance value and the voltage, we would have got this current later on, and that is what we would have found out. But in no case we would have found out the individual currents. You can get the individual current only by applying the concept that the voltage across this is voltage across that. That means I1 into R1 is equal to I2 into R2. Yeah, that's it pretty much. So if you have many resistances in parallel, even more, R3, R4, then the effective resistance will be 1 by R effective would be equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4. And let me emphasize on one fact over here. Like a resistance can be in series with some other resistance, in parallel, a resistance is not in parallel with some other resistance. It's a branch which is in parallel to the other branch. The branch may have one or more resistance. Meaning to say, I may have a situation like this, R1 in parallel to R2 and R3, which is in a branch. So we won't say R2 is in parallel. The current was coming over here from here and it was exiting from there. So we won't say R1 is in parallel with R2. R1 is not in parallel with R2 alone. R1 is not in parallel with R3 alone. The branch of R1 is in parallel with the branch containing R2 and R3. So that branch resistance we have to find first. So in this case, these two are in series. So that branch resistance is R1 plus R2. So if we apply the formula of 1 by R equivalent, it will be 1 by the first branch resistance, which was only R1 because that was the only resistance present over there, plus the next branch resistance. So if it is too complicated, you do it somewhere else and then put the value. It is quite simple. So I'll just write it as R2 plus R3 because those two were in series. That is how we'll get the equivalent resistance. So you have to identify very clearly from where a parallel branch starts and where the parallel branch ends. So I'll ask you some questions to check out whether you can identify things in series and parallel or not. So that is going to be on the board next. You may take a break. But before that, few simple questions to check whether you have got the concepts right or not. So now we know that when the resistances are in series, what we need to do, and when they are in parallel, what we have to do to simplify the circuit. But then how to ensure whether the resistances what we feel are in series are actually in series or not, or the ones which we think are in parallel, are they parallel or not? So I'll tell you a few checkpoints what you can look forward to. First, resistances in series. So say this resistance is in series with the other one. R1 is in series with the other one, R2. Why do we say these two are in series? The current, say I, which enters R1 and exits R1 has to totally go through R2. That current should have no other paths, and it should fully go through R2. It shouldn't be that a part of current has gone somewhere else. Then the two resistances are not in series. Like if I complete the circuit, these two resistances are in series. Even if I have say a resistance hanging over there, but then it's open circuit, a resistance over here, but then again it's open circuit, so the current can't enter into this. It can't enter over here. It has to totally go through R2. There is no other option. Hence, R1 will be in series with R2. Now let us discuss combination of resistance of branches which are in parallel. So say from a high potential point, current is coming and it has got options of splitting into various paths to reach its destination, and then again getting pumped back to a lower potential point. So that's the positive of the battery, and say that's the negative of the battery. Now here the current which was coming I has got split into three branches, and say the currents were I1, I2 and I3. Here we can see that this I3 has got no other option but to go through these three resistance and come back as I3 over here. There was no other path to go anywhere else. Similarly, I2 has to come back over here as I2, and I1 has to come back over here as I1, and the three are combining together as I1 plus I2 plus I3, which was equal to I. So the current which has split, if they are joining back, then for sure the resistances are in, or the branches are in parallel. So here the parallel branches start here, here and here. So one of the parallel branch is this. The other parallel branch is this. And the third parallel branch is this. So these three branches would be in parallel. So the effective resistance of this combination would be 1 by R equivalent would be 1 by resistance of branch 1 plus 1 by resistance of branch 2 plus 1 by resistance of branch 3. Now resistance of branch 1 is the resistance there itself, say small R1. So that's your R1. So this is R2 and R3. So this capital R2 would be R2 plus R3 because R2 and R3 are in series. Why they are in series? Because the current entering R2 has no option but to totally enter into R3 and come out. So the current entering here is I2, enters as I2 in the other one. Hence the two are in series. Similarly, branch 3 has got a resistance of R. Say this one is R4, R5, R6, R4 plus R5 plus R6, that's your R3. So we see that this bunch of resistance is effectively one equivalent resistance of this value. Now if I tweak this above circuit a bit and make it look like this, everything pretty much the same. There is R1, R2, I'm going to draw R3, and then there is R4, R5, R6. And now what I'm doing is, instead of joining R3 to the junction point, I am making a connection over here, and that's your R3. The high potential was this side, low potential is this side, and the current has to rush to that side. Now can you tell me what all things are in parallel and series now? So we have to comment whether R1 is in parallel with R2, R3 or not, whether R2, R3 are in series or not, whether R4, R5 and R6 are in series or not. So let us look at it very carefully. Now what do you think? Is R5 in series with R6? Is R5 in series with R6? The answer is no, a big no. They are not in series. Why they are not in series? You can see the current which was entering. So let me call them again as I1, I2, I3. Mind you, these I1, I2, I3 would be different from the earlier ones. Not I1, but still. So the current which is going through R4 and R5 is I3. I3 passes through R5, and we are wanting to find whether R5 and R6 are in series or not. R6 and R5 will not be in series now because the current which is passing through R6 is not I3. It's not I3 alone. I3 has come to this junction point and then has combined with some other current which was I2 coming from the top branch, and what has gone into R6 is I2 plus I3. So the current which was going through R5 is not totally going through R6. Some other current is going. R5 and R6 are not in series. So if you see things one next to the other, they may not be in series. Okay. Now, is R1 in parallel to R2 and R3? Again, they are not in parallel now. Why? Because they have split. The parallel branch has started over here, but then those branches are not meeting. This R1 branch is going this way and I2 branches come over here. So they are not in parallel. Is the bottom branch, is this branch in parallel to that branch? The answer again is no. This will not qualify till here as a branch. This goes as far as this and then ends. That's a branch. That is not in parallel to that branch. So the current which has split over here as I1 and I3 are not meeting at a joining point. There is no joining point. Where we can find a joining point is this branch number 2 and branch number 3. These two branches, they look in parallel. R2 and R3 are in series, or they are still in series, because whatever has entered into R2 is going through R3, which is I2 current. So these two resistances can be combined as one. And these two resistances again are having the same current going through one another, and hence they can also be combined as one. So R2 plus R3, which were in series, are in parallel with R4 and in series with R5. So fortunately that's just an addition. So this is in parallel with that. To solve that, you'll have to do 1 by R equivalent is equal to 1 by R2 plus R3 plus 1 by R4 plus R5. Now once you have done that, these two branches will reduce to a single branch to a single resistance somewhat like this, a single value, which is a combination of these two. Now that single one would be in series with this because all the current through this is going through that, and hence that will become a single value which can then be combined to the upper one as parallel resistances. So that is how you have to take. You have to be sure of which two are in parallel or series, combine them, go step by step. Don't have to take the whole circuit in one go. Many a times it would be impossible to do the whole circuit in one go if it's a decent circuit. If it is a very simple one, you might be able to do. If things are straight away in parallel and in series, you would be able to do. But then if combining them reveals the next step, you rather go step by step. Another important thing to find out the effective resistance of a mesh of resistances or a mesh of resistors would be to know where is the entry point of the current and where is the exit point of the current. If that is not known, then you can't tell what is the resistance of the circuit. Like if I say that there are 4 resistances like this, what's the effective resistance? That's an absurd question. That doesn't qualify to be a question at all, because we don't know from where to where the current is going. In fact, I'll solve one for you and ask you to solve others. So you see, both of this mesh is same. Say all the resistances drawn are 2 ohms. All of them are 2 ohms. If I ask you what's the resistance of this mesh or that mesh, it all depends on where the current is coming from and where it is going. So if I ask you what's the resistance of RAC, means current entering from A and exiting C or vice versa, is very different from asking you to solve RAB, where current is entering A and exiting at B. Now what's the difference? The current comes into A, splits over here. Current comes from, say, the higher potential A and tries to go to C, which is at the lower potential. So first it splits. By symmetry we can say it's the same, but let me call it as I1 and I2. Most probably I1 and I2 are going to be the same because there is no choice over here of taking the easier way, because no one way is easier than the other. So it has to be equal. Now these two currents are going to go in these branches like this and join over here. So we can safely say that this resistance will be in series with that resistance. So if this is 2 ohms and that is 2 ohms, I can redraw the circuit, that part, as this was your point A, that's your point C, and this is the redrawn circuit where B is somewhere here, but 2 and 2 have combined and I'm calling it as a 4 ohm. Can I safely call it as 4 ohm? Yes, I can, because this 2 is definitely in series, because I1 current entering this 2 ohm has to enter the other one. Similarly, these two branches combined, these two resistances combined is a single resistance like this, whose value would be again 4 ohms, as this is 2 and that's also 2. 2 plus 2, 4. Now clearly we can see that these two resistances are in parallel. So now we can apply the concept of parallel resistances and figure out how much is the equivalent resistance. How much it would be, we very well know it would be less than either of them. Both are 4, it will be less than 4. In fact, we can say that it will be half of 4. Can you tell me why? Because if there was only 4, only one of the resistance, then the current would have been something. If I put the other resistance with the same potential difference, the current in the other branch will be the same as the earlier one. That means the current would have doubled. If the current has doubled with the same potential, we can safely say that the resistance has become half. Anyways, you can apply the formula and get it. 1 by R will be equal to 1 by 4 plus 1 by 4. And when you do the math, you'll get it as 2 ohms. Now here again, if I have to solve this circuit, then it's not same as the earlier one. The entry point is A and the exit point is B. So the redrawn circuit would not be the same as the first. Entry point is A and exit point is B. You may draw the simplified version before I do. So one branch is going from A to B. It is having a resistance of 2 ohms, the original one. The other branch, we can see the current will enter from A split into 2, say I1 and I2. Definitely this time I1 is not equal to I2. Why? Because this path is having much more resistance. So what can we say? Is I2 greater or I1 greater? I2 has to be less than I1 because more current or more electrons will choose to flow through the less resistive path than the higher resistive path. Nevertheless, some would flow. If in fact if these are all same, then the amount flowing into other one will be 3 times more than the amount flowing in the first one, because the resistance of the first one is 3 times less than the resistance of the other one. Why 3 times? Because these 3 resistances now are in series. Whatever has gone into this branch from A to D, the same current has to go from D to C and the same current has to go from C to B. So all these 3 become 1. So making them as 1, I'll make a curve and it goes back to B. So it's a single resistance. How much would be the value? It would be 2 plus 2 plus 2, which is 6 ohms. Now what do you think? What's the next step? Now we can easily see that these two are in parallel. So making them as parallel, making them into 1 as parallel, what we get is a single resistance whose value is lesser than the least of them, which is less than 2. So it is again going to be given by the formula 1 by R is equal to 1 by 2 plus 1 by 6. How much would that be? So that would be equal to 12 by 8, which is equal to 3 by 2 ohms. 3 by 2, that's 1.5. Is that less than 2? Yes, it is less than 2. Most probably our math would be right. If you are going wrong in our calculations, this won't give an answer in the expected range. The expected range over here was less than 2, between 0 and 2. If this resistance was very very high, it would have been nearer to 2. If this resistance was 2 itself, it would have been half of 2, which is 0.5. If this resistance was 1, less than 2, then it would be the lesser of the 2 is 1 now. So lesser of the least. So answer would be less than 1. Now I would like you to solve these 3 circuits. In the first one, I would like you to find the resistance between A and C. In the next one, the resistance between A and B. If I say what's the resistance between A and B, I am saying that the entry point of the current is A and the exit point is B. And in this one, R, B, D, star mark this one. So in the first one, current has to enter from A and leave from C. So what are the options for the current? Which all paths it can take? It can take this path, it can take that path, it can take that path. Going through all these paths, they are going to converge at C. So we can see that the current has branched out into these 3 branches. Are the 3 branches in parallel? Yeah, they are, because whatever current has entered them, the same currents are meeting back again. Now, are these 2 resistances in series of each other? Yes, they are, because whatever has entered this is going through that. Hence, a simplified version of the above circuit is this, where this is point A, this is point C. This lower one, 2 resistances, I have combined as a single one as 4 ohm. The upper 2 also as single 4 ohm, and in between remains 2 ohms. So these 3 are in parallel now, and your answer would be given by 1 by R is equal to 1 by 4 plus 1 by 2 plus 1 by 4. Now this particular one, what I would do is, I will say this 4 and that 4 are in parallel, and I'll forget about the 2. Is it true that the 4 and 4 is in parallel? Yes, it is. So what I can say is, the 2 ohm guy remains and the 4 and 4 in parallel has become a single resistance. How much would that be? 4 and 4 will yield me 2 ohms. That was oral calculation, hence I did it like that. Now we have got 2 and 2 in parallel, and the 2 and 2 is going to give me how much? it is going to give me 1 ohm. So the answer would be 1 ohm. If you had done like this, you would still get R is equal to 1 ohm. Now in the other one, where the current is entering from A and exiting B, let's see the things which are in parallel and which are in series. The current has 3 paths to go. This is the shortest, looks like the shortest path. This one goes, the current goes like this, can't go back, no, can't go back. The target is here, this is the draining point, this is the lower potential point, so it goes like this. So that's one path. The other path is, it goes into this and goes over here, joins the other current and marches to B. And the first path is in this lemon yellow, it goes to B straight. Now what resistance is in series or parallel with what? Is this resistance in parallel with this? No, they are not. The branching point is same, but the meeting point is not there. So they are not in series. Is this resistance in series with that? Yes, they are. So we'll do that first. Is this in parallel with this? No, they are not. This one is not in parallel to this. This one is in parallel to the whole branch. Is this one parallel to that? No, they are not. So we have got nothing as parallel over here. You can take your time and see again, there is nothing in parallel over here unless until we combine these two and make them as a single resistance. And once they are made as single resistance, we can see that this branch is in parallel to that. So the next simplified step would be, there is the 2, earlier 2 remains as 2. This is the in between 2, remains as 2, and that one also remains. These two combine and you can call it as a 4 ohm resistance. Current was entering here, current was exiting there. Now we can easily see that these two are in parallel. They are branching and they are meeting. The same current which has branched out has met. So these two can be made as a single resistance in between, which will be lower than both of them. So we can cancel out this resistance, cancel out that, and this resistance is there now with us, which would be equal to 4 by 3 ohms by doing a parallel of 3 and 4 ohm resistance. So now we can see that the current which is going through this 4 by 3 resistance has to fully go through this 2 resistance. Hence, your 4 by 3 would be in series with the 2 resistance, with the 2 ohm resistance. So the combined value would be 4 by 3 plus 2, which will give you as 10 by 3. So you'll have this original 2 ohm in parallel to 10 by 3. So your final answer would be 1 by R is equal to 1 by 2 plus 3 by 10. So that's 5 by 10 plus 3 by 10. So that's 10 by 8, which is 5 by 4 ohms. That is 1.25 ohms. So you see that this answer is quite different from the other one, because the entry and exit point was different. One more thing I'd like to point out is, no matter what is the answer is always less than the least resistive path. So what do you think was the least resistive path in this? I think the least resistive path was from A to C directly. So that's that path. How much is the resistance? 2 ohms. Your answer is going to be less than 2 because you have got other alternative paths. Hence, your answer, your total resistance would be less than 2, which is true. It is coming as 1. Here also the least resistive path was this, 2 ohm. This path alone was 2 plus 2, 4, which is not happening that way. And this path was 2 and 2 and 2, which was 6. Least resistive path was this. Your answer would be less than that. So answer comes less than 2. Now the last one, I put a star mark over there for a reason, BD. So it enters B, it exits D. Now what do you think are in series and parallel? None of the resistance are in series to any other resistance in this. None of them are in parallel to any other. So you can check out with the concepts told to you. Here the splitting is happening, but they are not joining. This current in this doesn't go totally into this or that. So nothing is in series, nothing is in parallel. How would you do it? This particular one can be done as a Wheatstone bridge. So we'll talk about that later. But otherwise, it can't be done as combination of parallel or series resistances. This question fortunately has got such a ratio of resistance that the one here between A and C can be removed, and then the question becomes an easy one: 2 and 2 in series, 2 and 2 in series, and both of them in parallel. So I hope you are ready to take a quiz on simplifying resistances. Now we know how to identify resistances in series and parallel, but still they can make the circuits quite tricky, particularly by having edges, long wires which are not necessary. Let's resolve such circuits.